Hi. This may look like a very complicated specification, but all it's really asking for is cutting a vector into two parts. And we specify the length of one of the two parts. The other one is just the rest of the elements. We want either the first n elements grouped and then the rest of them in the second group, or we want the second group to be the last n elements and then the leading elements up to that form the first group. And the way we determine if we want the first or last is by the sign of this number. So a positive number, we specify the length of the first group, and a negative number specifies the length of the last group. This kind of specification is parallel to APL's take and drop primitives. So the take primitive can take the first three or take the last three. And similarly, we can do drop the first three and drop the last three. This pretty much gives away how we can solve this problem. So if you take the positive case first and make a little lambda, where the left argument is alpha and the right argument is omega, we can see here that we want the first three elements, and then we want the second group to have the first three elements removed. However, if we flip the sign here, then our groups come in the wrong order. We can fix this by reversing. But we don't want to always reverse. We want to conditionally reverse. One way we can do this is by using the power operator. Power operator takes a number on the right, and that number is the number of times we want to apply this function on the left. How many times do you want to do it? Well, we want to do it 0 times if the left argument is positive, and 1 time if the left argument is negative. Luckily, APL comparisons return 0 or 1 for false and true. So if 0 is greater than the left argument, that gives 0 in this case, we reverse 0 times. And if it is true, then it gives a 1, and we reverse once, which solves our problem. But we can make it a little bit more elegant by observing that since we only have 2 elements in our array, reversing is the same thing as a one-step rotation. So we can try this. The dyadic form of the same symbol is the rotation. So here we've rotated one step, and if we have a positive number on the left, we want to rotate 0 steps. And that means we can use the same expression whether 0 is greater than the left argument in order to find out the rotation amount. This function can be converted to a tacit or point field form. We can observe here that we have a pattern. We have these 2 arguments that are applied with one function and with another function, and then there's an invisible function that binds them together, which is the stranding into an array. But stranding into an array is actually concatenation of the enclosures. So if we do a concatenation, but pre-process both arguments with an enclosure, we get the same exact thing. And now we can make a proper fork. So what happened here is that we removed the explicit mention of the arguments to outside this little function. And so these are 3 functions, 1, 2, 3. the arguments are used on the left and the right function, and their results are combined using the middle function, which is the stranding together function, pairing function, concatenation of the enclosures. Here we have 0 is greater than the left argument. So now we can go through and convert this whole thing to a test function. 0 is greater than the left argument here, right argument here, and we finish off with our tested function. However, this inner function is being applied to the result of taking the left argument and the right argument. That doesn't add anything, so we can strip off that outer level. And here's our final function. Thank you for watching.